Okay there, young students of chemistry. This is a short recording regarding colligative properties. So here's the thing. It's, substances by themselves have, for a given temperature and pressure, for normal temperature and pressure, constant freezing points and boiling points. We know that water at standard temperature or standard pressure is going to boil at 100 degrees Celsius and freeze at 0. And unless we change the pressure, that's not going to change the temperature of boiling and freezing for water. A colligative property is a property of a substance that changes because we've dissolved stuff into it. And you can kind of think of the stuff that's dissolved into the solution as getting in the way of the solvent particles or causing some attractions that weren't there before. So the definition of a colligative property is that it is a property of a solvent. It is the solvent that is changing, not the solute, as we add solute to the solvent. The colligative properties depend on concentration, and the more concentrated the solute is, the more that property changes. So for dilute solutions, the property will change a little bit. Concentrated solutions, it's going to change a lot more. So there are 3 colligative properties: boiling point, freezing point, and vapor pressure. We're going to be doing calculations for boiling point and freezing point, but we are not going to be doing calculations for vapor pressure. And you can see that the boiling point of a pure substance, let's just take water for example, is going to be lower than the boiling point of a solution of water. So you add some salt to water. The boiling point of the salt water is a higher temperature than the boiling point of the pure water itself. Freezing point depression, that tells us that freezing point is going to go down. So salt water has a lower freezing temperature than pure water does. And this is true for all solvents. I'm using water because that is the most common solvent. But if you add solute to a solvent, the boiling point is going to go up. The solution is always going to have a higher boiling point than the pure solvent alone, without anything dissolved in it. Okay, so how do we calculate the change in the properties? It's a very simple equation. It is delta T is equal to K times M, where delta T is the change in temperature, and we're going to calculate that for boiling point or freezing point. So how is that boiling point going to change? How is the freezing point going to change? K is a variable that stands for the boiling point or freezing point constant, and it is important that you remember that is the solvent that is changing, not the solute. And this is a value that you can just look up. In your textbook, the values for boiling point and freezing point constant are on page 494 and 495. Or, you can just ask your telephone genius, right? Ask Siri or Alexa or whoever it is that you ask the boiling point constants for certain substances. Normally it's water, so you might want to record in your notes the boiling point and freezing point constants for water. So for water as a solvent, the freezing point constant, we would say that is Kf, is 1.86 degrees Celsius per molal solution. And the boiling point constant, we'll call that K sub B, is 0.51 degrees Celsius per molal solution. If you have a solvent other than water, just look up the freezing point or boiling point constant. And then M stands for molality. Remember that you learned when we talked about solution concentrations that a molal concentration is moles of solute divided by kilograms of solvent. So to get the change in temperature, we multiply a constant that we look up times the molality. And of course, if we're not given the molality, we're going to have to calculate that. So here's the thing that we have to be concerned about. When we have a molal solution, if our solute is an ionic solute, remember that ionic compounds dissociate in water, whereas covalent compounds do not. So the dissociation of the ionic compound is going to change the number of particles that are in the system. And you can see that what I have here is a dissociation representation for magnesium chloride. If we have a magnesium chloride solution that's listed at 1 molal, it will dissociate into magnesium ions and 2 chloride ions when it goes in the water. So a 1 molal solution makes 1 molal of magnesium ions plus 2 molal of chloride ions. So we cannot say that the molality of a magnesium chloride solution is 1 molal. We have to consider the fact that that dissociates. So we end up with particles. The total number of particles in the solution is 1 molal plus 2 molal, which gives us a 3 molal solution. This is what we call the Van't Hoff factor. It's abbreviated with an I. And for magnesium chloride, the Van't Hoff factor is 3. This is the number that we multiply the molality by before we put it into our freezing point, depression, or boiling point elevation, before we put that into the calculation. So very quickly, we can look at a compound formula, and once we've determined that it's ionic, because remember, covalent compounds do not dissociate, we can just look at the subscripts to determine the Van't Hoff factor. If you look at the subscripts of magnesium chloride, the subscript on magnesium is 1, the subscript on chlorine is 2, 2 plus 1 is going to give us a Van't Hoff factor of 3. So if we look at the calcium hydroxide, the Van't Hoff factor here is 1 calcium plus 2 hydroxides. 1 plus 2 is a Van't Hoff factor of 3. For the aluminum oxide, we have 2 aluminums and 3 oxygens. 2 plus 3, and of course that Van't Hoff factor is 5. Be really careful with these. Remember that this is a polyatomic ion. CO3 is a polyatomic ion. So students often look at that and they're like, oh, the Van't Hoff factor is 5. Oh, the Van't Hoff factor is 4. You know, because they'll go, oh, 3 oxygens, 1 carbon, 1 calcium. But remember, ionic compounds only have a positive ion and a negative ion. In this compound, the positive ion is calcium, and there is 1 of them. The negative ion is carbonate, and there is only 1 of those. So 1 plus 1, the Van't Hoff factor here is 2. Okay, I'm going to take a minute to do just a problem or two with you, and I'm going to move along pretty quickly here. And then you can do your problem set that's at the bottom of the page. So it says, how much will adding 2.65 moles of sugar decrease the freezing point of 2.5 kilograms of water? So sugar is our solute. Water is our solvent. It is the water that is changing. And we want to know how these properties are going to change. We know that our equation is change in temperature is equal to K times M. And then, if we have an ionic solute, we have to multiply the M by the Van't Hoff factor. Sugar is not an ionic solute, so we can ignore the Van't Hoff factor here. We need the molality. We know that molality is moles of solute per kilogram of solvent, so 2.65 moles of sugar per 2.5 kilograms of water. And that's going to give us a molal concentration of, I think, about 1.06. Let me chug that out in my calculator here. Yep, 1.06 molal. So if we want to know the change in temperature of the freezing point, we're going to use the freezing point constant for water, our solvent, times the molality. The freezing point constant for water, you put in your notes, is 1.86 degrees Celsius per molal. And we just calculated the molality to be 1.06 molal. That's going to give us a change in temperature of 1.97 degrees Celsius. So if we wanted to know, hey, what is the new boiling point of the or freezing point of the sugar water, we know that the colligative property is freezing point depression, which means that the freezing point is going to be lower than the normal freezing point of water. If the normal freezing point of water is 0 degrees Celsius, we're going to subtract the 1.97 because it is freezing point depression. And that means that we're going to get a new freezing point of 1.97 degrees Celsius. We can follow the same course of action for calculating the boiling point. However, instead of using the freezing point constant, now we're going to use the boiling point constant. So Kb times the molality, the boiling point constant for our solvent, water, is 0.51 degrees Celsius per molal, and our calculated molal concentration is 1.06. You can see here that the unit molality cancels. And then, of course, just multiply. We have it's not right. We have a change in temperature of the boiling point of 0.54 degrees Celsius. The colligative property is boiling point elevation. So we are going to add our change in temperature to the normal boiling point of our solvent. Since our solvent is water, we know that its normal boiling point is 100 degrees Celsius. So we're going to add the 0.54, and we end up with a new boiling temperature of 100.54 degrees Celsius. Let's consider a situation where our solute is not a covalent solute, but is an ionic solute, and that's what we have here. We're using the same amount, but this time our solute is sodium chloride. That is ionic. Sodium chloride dissociates into 2 ions. The Van Hoff factor there is 2. 1 sodium, 1 mole of sodium, and 1 mole of chlorine. 2,500 grams is 2.5 kilograms. So notice our moles and our kilograms are the same from problem 1. So our molality is 1.06 molal. However, because our solute dissociates, we're going to have to double that when we put that into our change in temperature equation. So change in temperature is equal to the constant times the molality times the Van Hoff factor, because our solute is ionic, and ionic solutes dissociate. So it's the same calculation. However, we have for the freezing point 1.86 times 1.06 molal times 2. So it's going to change our temperature by twice as much as the sugar did. So we're going to get 3.94 degrees Celsius change. We know that it's freezing point depression, so the normal freezing point is 0 for water. That's our solvent. The new freezing point is negative 3.94. We could do the same thing for the boiling point, except we're going to use the boiling point constant for our solvent, water. And our new boiling temperature is 101.08 degrees Celsius. So, like, when you consider an ionic solute versus a covalent solutes are always going to change the colligative property less than an equal molal ionic solutes. Let me say that again. If we have two solutes, two solutions, equal concentration, 1 molal, if one of those solutions is made with a covalent solute and the other is made with an ionic solute, the ionic solute is going to change the colligative property more. The boiling point will be higher in the compound that has the ionic solute. The freezing point will be lower in the solution that has the ionic solute. All right, there you have it, colligative properties.